All right, we're going to go ahead and get started. So welcome everyone to today's webinar on engineered reliability for critical thin film conformal coating practices to safeguard your electronic product design. My name is Stephanie Fauché and I'll be your moderator today. And I'm joined by Dusty Askin, who is the Senior Director of Process Engineering at HCO. A few quick housekeeping notes before we get started. At the bottom of your screen in the right-hand corner, you'll see a Q&A box as well as a chat box. Feel free to use this to share your questions with us throughout the presentation. We will be covering them in the Q&A at the end. You can also reach out to us with any issues with audio or the screen sharing via the chat. We will be recording today's session and it will be sent out along with the slides after the presentation. And without further ado, I'm going to hand that over to Dusty.
Hi, everybody. Welcome. Thank you for your time today. As Stephanie said, my name's Dusty Askin. I've been with HCO for about 6.5 years, where I lead the process engineering team. I got my bachelor's degree in engineering physics, which is basically electronic materials, from the University of Pittsburgh, and my master's in biomedical engineering from the University of Utah. I spent the bulk of my early career developing implantable medical devices, like brain implants, looking for materials to protect electronics from the environment inside the human body. And at HCO, I've been helping customers to find solutions to their own environments. I'm involved in work on all the aspects of problem solving, from speccing the coatings, determining the masking, the physics and chemistry of the coating itself, and some failure analysis when developing processes. This webinar will cover an overview of conformal coatings, both traditional and thin film, coating properties critical to your design, and some tips for best practices and design. So as Moore's law increases the density of semiconductor design, chips and electronics increase in complexity and decrease in size. The closer together these components and traces become, the less moisture and liquid is required to cause shorts and corrosion. There will be an expected 55 billion connected electronics deployed by 2025. That's diverse sensors and wireless devices, computers, controllers for all aspects of our infrastructure and our lives. Those devices are expected to survive in a world which is not terribly hospitable to electronics, though. This reality necessitates designing for common environmental hazards: simple humidity, puddles, precipitation, spilled beverages, urban air quality high in sulfur and other corrosive elements. Computers used to sit on desktops. Now they've evolved to managing and facilitating critical infrastructures that are outside in harsh environments. Unprotected devices will fail in these operating environments. And in addition to safeguarding against failure-inducing conditions commonly found in the world at large, we're increasingly relying on high reliability electronics in failure-critical applications, automobile airbags, operating room equipment, where simple corrosion can be catastrophic. In order to have a great design, you need to be prepared for the unexpected. The items on the left are well understood and incorporated into the design at the start. Everybody's concerned with cost effectiveness, with sustainability. Product features are part of the key design inputs that you have. But these are balanced against the items on the right, which are often unplanned for. They're varied by nature, and they can lead to unexpected failures. So designing in reliability and protection can help to mitigate the unforeseen. For corrosion to occur, you need 3 things: a voltage, ions, and water. And you can have as little as a few molecular layers of water. It doesn't take very much for the ions to be able to move. Most folks in this webinar are probably familiar with corrosion-induced failures, especially those that have inspected field failures. But here we're going to give a few examples. In example 1, we have creep corrosion, or molecular migration as a result of sulfur reacting with copper or silver on the leads of your device typically. This results in an unstable PCBA over time. It's a critical issue when you have a PCBA that's essential for the function of a system. And it's also non-repairable, driving up the cost of replacement for a given product. Creep corrosion can lead to dendrites, and that's the migration of ions between 2 things leading to it grows a chemical structure between the 2. These dendrites grow across the surface of the components or on the surface of the PCBA, leading to electrical shorts, which do result in failure of the PCBA and subsequent systems and product. This can be intermittent and latent due to the time it takes for this to fail. It can start as a high resistance short, which you might not notice because it mostly impacts just a signal, degrading the current slightly. However, over time, the density of the dendrites increases, which reduces the resistance until full failure occurs. And there on the right, we have an example of wholesale corrosion as a result of submersion. You can see the growth of a number of chemical products, byproducts, the reactants, or the reaction products of electricity interacting with salt water and the metals native to the board. The PCBA is damaged beyond repair and rework is not possible in this case. The above are largely limited to exposure to minor environmental moisture, other than the full immersion there at the end. But these are just a few of the failure modes a coating can help to protect against. It's a bit of an outline of the entire presentation we have here. The topics for the remainder will touch on the following. One, breaking from traditional design or traditional protection methods, an introduction to newer thin film coatings, critical properties to consider when speccing your conformal coating, vacuum deposition and how it creates desirable coating features, and the best practices to improve reliability and lifetime for your electronics. So in our first topic, traditional seals and gaskets and conformal coatings all have their place. They're often good enough, but as component and device density has increased, they're running up against limits. Additionally, what appears to be a cost-effective solution from a materials standpoint can have downstream impacts to field failures, returns, and overall cost of ownership. So here in Bubble 1, we have mechanical seals and gaskets. They're inexpensive. They can be designed in as part of the device housing and mechanics. You can have just your mechanical engineers handling this. You don't need to worry about an extra conformal coating or reliability engineer. And they start off completely excluding bulk water. They're generally fairly successful right out of the gate, but they do degrade. Adhesives and form-in-place gaskets eventually lose adhesion. They soften in heat and are not effective after disassembly and repair. Gaskets and mechanical enclosures can crack, age, loosen over time. They suffer from temperature fluctuations, so they no longer seal as well as they did when they were first put together. And moisture and gases can eventually get in because most of these things are typically polymers or rubbers in nature. All of those breathe slightly. You're going to have gas ingress, you're going to have moisture ingress, which eventually collects inside the device. Traditional conformal coatings, which we all know, silicones, acrylics, urethanes, things like that, they're generally inexpensive. Though the more features or specific engineered properties you want to have involved, the more cost you're going to have. They can be bulky. They can add significant thickness and weight to a board. Conformality can be inconsistent because the material is wet differently on the surface. You'll get slight air bubbles. You don't get full wetting. You'll get voids around the edges of small components. And they often involve solvents or have to go through a reaction in order to polymerize. And some of those byproducts are generally toxic. So you have to consider that on your production floor, if not in the finished device. The traditional application methods for conformal coatings, it's typically simple and robust, but it can be quite messy. And as much as an art as a science, you'll have certain operators that are better at running that spray gun. You have to move things through the dip coating at particular rates, and it's not always predictable. Application methods such as brush or spray can leave inconsistencies, which are openings for liquid and gas contaminants to get into the product. So they do have limitations with the low-tech and cheap application methods down the road in your finished product. Just to dive in on conformal coatings from a higher level standpoint, why do you need conformal coatings? They may be for protection from the environment. It could be secrecy of components and designs. You may need an opaque conformal coating to hide your design from competitors. Mechanical reinforcement of solder joints or other aspects of the board. Overall survivability. You want your board to not need field servicing for the length of its product life. I already mentioned the broad product families. Traditional conformal coatings include acrylics, epoxies, silicones, urethanes, sometimes blends of those four, or relatives of them, such as acrylates. It also includes parallenes. Parallenes have been around for about 50 years and are typically lumped in with all of these more traditional conformal coats. How are they applied? We covered this briefly previously, but traditional coatings can be a 1-part or a 2-part. They're almost always a liquid. You can spray them, dip them, dispense them, and all of that can be done in line with your other manufacturing processes. But it does leave a risk of bubbles, voids, and wetting problems. Parylene is the outlier here. It's a vacuum deposited material, which is by necessity a batch process, but the vacuum coating does have strengths, which we'll cover in the next few slides. How do you choose which conformal coating is right for your application? In my experience, conformal coatings tend to be an afterthought. They're added when you have mechanical or electrical or environmental failure that starts to occur. It's to fix issues with the overall design or the overall use case that weren't anticipated at the start. You need a conformal coating that solves your problem. It needs to wet adequately and be compatible with your substrate materials, and it needs to meet your standards, whether those are military, medical, FDA, automotive, UL. Most of those standards organizations do have something that addresses conformal coatings. There's a balance of cost and performance. And at the end of the day, it has to fit into your handling and manufacturing process. Is your contract manufacturer set up to handle coatings for cleaning prior to coating, for the inspection that comes with it? It's a fairly specialized bit of manufacturing that goes into putting a conformal coating onto a PCBA. To dive a little bit more into the broad families, the traditional conformals are acrylics, which have good electrical properties and are easy to remove with solvents, so they're fairly reworkable. Epoxies, which are typically 2 parts. They're very strong, a little bit difficult to rework, sometimes have thermal mismatch or mechanical mismatch with the substrates, but often add a lot of strength to your board. Silicones, we all know these to have really good chemical resistance. They're preferred for medical applications because they tend to be fairly biocompatible. They can be more expensive though, and they're a little bit more highly engineered than some others. Urethanes have many of the same strengths as silicones, but are a little bit difficult to rework themselves. And paralenes. These are the gold standard and the only thin film coating included with traditional coatings and standards over the last few decades. They are lightweight, solvent-free, and these are applied at a fraction of the thickness of traditional materials. As I mentioned, traditional materials tend to go down fairly thick, so for an effective coating, they're typically in the 50 to 250 micron, or 2 to 10 thousandths of an inch. But I often encounter them in the several millimeter range. To contrast, the thin film materials we'll cover shortly, including parylene, are generally referring to coatings under 20 microns, or less than a thou or a mil, and those can be as thin as 500 nanometers. So let's look into some of these technologies. So thin films and nano coatings are a broad grouping of materials, but they're generally applied under vacuum. Vacuum deposition gives us a number of strengths and challenges. Vacuum deposition is a batch process, as I mentioned before, and it's not suitable for all components, though in my experience, it works for most electronic components. Vacuum deposition does require more advanced masking than liquid coating, just because we're talking about molecules here that can get into a smaller space. Low pressure molecular flow in the vacuum means that it's much more conformal than liquid coatings. And building the coating molecule by molecule on the product means that you have a much more uniform coating as well. And I'll get into more of these in detail as we go along. I'm going to address the 3 major classes of thin films encountered outside of semiconductor processes, though, here. So parylene, as I mentioned before, it's deposited using a chemical vapor deposition process, or CVD. The coating is polymerized from a reactive monomer. It enters into the vacuum chamber from a thermal delivery system, which makes Parylene just a little bit different than some of these other coatings we're going to talk about. It's considered the gold standard, as I mentioned. First found widespread use in aerospace applications in the 60s, where weight and reliability were critical. While the basic physics and chemistry are the same as those original films, there have been advances in chamber and furnace design, precursor purity, process control, and the various chemistries that are available that have really expanded the capability of this method and made it a lot more cost effective for markets outside of aerospace. Coating is dense and uniform. It's a long chain polymer. It's completely conformal on the substrate. The molecules can penetrate into micron-sized gaps, so we can get under BGAs and coat the solder balls and surrounding leads without leaving any voids. Parylene also comes in a variety of flavors. So from the more common C or chlorinated Parylenes, which many of you may have encountered on typical products, and N, which is a halogen-free. There's also fluorinated varieties that can handle higher heat. Those are labeled as VT4 and AF4. These are just the most common flavors that are available, but there are others out there that are more specialized chemistries. Moving on to plasma applied nano coatings. These are deposited using plasma enhanced or PECVD. So it's just another subset of chemical vapor deposition. It also happens in a vacuum chamber. You can either create a remote plasma to create polymerizable species outside of the deposition chamber, or you can create plasma in chamber to create species just above the board, which helps with polymerization in situ on the board. Plasma can facilitate a huge range of materials, from polymers all the way out to ceramics, using carbon, silicon, and metal oxide-based chemistries. Conformality ranges from line of sight to not quite as conformal as Parylene, and film density and protection levels can vary greatly, but surfaces can be functionalized easily. You have a lot more levers you can pull when it comes to a plasma applied nano coating, between chemistry, energy, pre-treatments, things like that. So you can get a pretty wide variety of chemistries on your substrate. And lastly, on this slide, we've got atomic layer deposition, or ALD, and it's a specialized form of PECVD. Materials are deposited from exotic gases as atomic layers with highly specific chemistry. It allows better access to metals and metal oxides than the plasma I discussed previously. The coatings are completely conformal, a la Parylene, but traditional thermal techniques are slow. So this is a higher temperature application process. Typically, it does go more slowly than either plasma applied nano coatings or Parylene coatings. But what you end up with, the best films are the densest achievable, and they make really good gas barriers. Beyond these, there's also another grouping of more, they're liquid nano coatings or engineered fluids. They're highly specialized solvent-borne coatings that are deposited more similarly to traditional dispensed or dip-coated coatings, and they're beyond the scope of what we're going to get into today because of the chemistries involved. So thin films, including Parylene and the range of chemistries possible with plasma and ALD, all have some broad features in common. Physically, they're thin. They provide equivalent protection to conventional coatings at less than 1/10 the thickness. Thin film materials are new to industry standards as a group, or at least to the ones that consumer electronics and industrial typically encounter. IPC, who handle a lot of the board manufacturing, many of you are probably very familiar with this group, only settled on their ultra thin, or UT, sub 25 micron material category in the last 5 years. Thin protection equals lightweight protection. They're uniform, both in chamber and on board. So you end up with a very highly repeatable manufacturing process. There's no operator variability, no differential wetting based on the temperature of the production floor. Because it happens in a vacuum chamber, it's always the same. They're either highly transparent because they're so thin, or they're optically clear. So a thin oxide layer is basically glass as far as we're concerned. So it tends to be a very good optically performing coating. Thin films are protective. So for a given unit thickness, thin film solutions give superior protection with less coating. They are broadly chemical and water resistant. They allow less water to move through them than traditional coatings, meaning they're less porous to the migration of water molecules. Parylene has a strong combination of flexibility, chemical, and moisture resistance. And plasma and ALD films can be tailored to a number of characteristics, particularly in regards to their gas permeability or surface properties. So you change precursor chemistry, you change the energy of the deposition, and you end up with a different material that meets your goals. Additional benefits, you can achieve tailored chemistry without changing the manufacturing process. Most of these materials have very good dielectric strength or insulation at comparatively lower thicknesses, which we'll discuss in the next slide. And thinner coatings create less problems with heat dissipation. So today, we're covering the 4 fundamental coating properties to understand to ensure success. Let's take a look at a few of these characteristics and how they'll bolster reliability. First critical property, dielectric strength. The dielectric strength is basically how good is this material at electrical insulation. It's critical for ESD and high voltage applications. We can see the real strength of parylene in this case. It delivers the same strength as epoxy and urethane at much thinner coatings. The metal oxide and ceramic films that plasma and ALD can make are potentially even stronger at thinner layers. The second critical property, thermal conductivity. So this is one of the things that traditional conformal coat can often be a problem. A big, thick insulating silicone layer on top of your board makes it so that you can't dissipate your heat. Your chips don't operate as efficiently, or they potentially even overheat. Thermal management's critical for your electronics. Small plus high power is going to equal a lot of heat. Whether it's direct coupling to a housing or radiating the heat away from a chip, a thick insulating material is going to hinder this, whereas a thin, fairly conductive polymer can allow better thermal management. And both of these are critical properties for designing your part from both an electrical and a physical standpoint. Moving on to our third critical property, keeping water away from the board, is resistance to corrosion. So the primary corrosion property is your water vapor transmission rate. If water can't reach the surface, corrosion can't occur. But all polymers, like I mentioned before, breathe a little bit. They allow moisture molecules or humidity, the molecular water, to pass in and out. What we need is a very low water vapor transmission rate, or WVTR. This doesn't solve all the problems, but it certainly slows down the ability of that water aspect of voltage ions and water to get to your board substrate and cause corrosion. The second corrosion property we worry about is water absorption. This plays a role in overall corrosion protection. It also affects your RF and wireless designs and performance. So when your dielectric coating on the outside of your antenna starts to absorb water, it can affect your RF properties. What we want is something with a very low water absorption rate. Parylene does this in spades and achieves a lot of what we're after here. Fourth critical property, chemical resistance. So this list includes both common manufacturing and cleaning chemicals, but they aren't dissimilar from everyday exposure items like gasoline, smog, sunscreen, a lot of the things that our products are going to face in the daily world. These solvents would very likely damage any electronics underneath the coatings. And a good coating is spec'd to handle both your handling and manufacturing in factory and the use case environments afterwards. Okay, moving on from the properties of the coating that you need to consider, the 4 properties, we're going to move into an overview of how these things are deposited and how it's going to impact your manufacturing process. So CVD, which is the one that's tied, non-plasma CVD, so just CVD generally, chemical vapor deposition, is a vacuum deposition process. It takes anywhere from 5 to 20 hours from door shut to door open, depending on the outgassing of the boards and how thick your coating needs to be. Most chambers are cylindrical. HZO happens to use a large rectangular chamber for better loading efficiency for our Parylene processes. It starts with a solid dimer precursor, which is illustrated on the upper left, which is sublimated at around 150 degrees C, passes through a pyrolyzer, they're on the upper right of the diagram, which is around 600 degrees C, and it cracks the dimer into two reactive monomers, which are then pulled into the vacuum chamber by the pump with the product inside, at which point those monomers are polymerized in situ, creating a coating on the product. In this case, there's no curing and the parts aren't in a furnace. This is in situ polymerization. It's room temperature. And the polymer is fully inert when it comes out of the chamber. So the polymer chains have fully reacted. There's no curing, there's no drying. Everything is protected fully when it comes out of the chamber. On the right, we have most of the process highlights. These are items that I've mentioned previously about Parylene. As I said, highly conformal. Because it's a vacuum process, it's very repeatable. It's a microns level application, so those molecules can integrate into even very small spaces, and you have very precise thickness control throughout the chamber. Moving on to PECVD, or plasma enhanced chemical vapor deposition. Plasma enhanced CVD is also a vacuum process, but the reactive molecules are created by plasma instead of by heating them up. So it's not thermal anymore. I'm now applying all of my energy through the plasma generation. Plasma can be generated remotely, as is illustrated here, or inside the chamber with the product if it's between two electrodes. Plasma activation of the species allows a very wide range of chemical precursors, silicons and silanes, hydrocarbons, fluorocarbons, oxides, and a limited range of metallics. Tuning the plasma parameters, as I mentioned before, such as frequency, power, electrode spacing, can also allow you a wide range of film densities and chemistries. Compared to more typical CVD, the life of the reactive molecules in a plasma chamber is a lot shorter because we're activating them with a RF energy instead of thermal. This means they aren't quite as conformal, but it also means the masking requirements are a lot less, sometimes less than traditional liquid conformals even. Compared to CVD, the deposition rates are also much faster. Effective coatings, depending on the overall end requirements, can be deposited in 30 to 120 minutes, protecting an entire chamber full of product. Plasma is a well-characterized tool for cleaning, improving adhesion, and surface modification for hydrophobicity. So this makes for a full all-in-one chamber solution, depending on the chemistries that you choose. Moving on to ALD. As I stated earlier, ALD is a subset of PECVD. It's relatively new to consumer electronics or electronics generally as a protection method, but it has been used extensively in semiconductor. For conventional thermal ALD, as seen typically in semiconductor, it's a relatively high temperature process, greater than 100 degrees C for the substrate. Most of our electronic PCBAs aren't happy about that. The chips don't want to be that warm. So we need to focus on finding a way of getting a lower temperature ALD. The way it typically works, though, is precursor A is flowed into the chamber from the first reactor, depositing an atomic layer on the product, say aluminum. Chamber is purged, and the atomic layer might be modified by a plasma to allow chemical reaction with the next layer. Precursor B is then flowed into the chamber, depositing another atomic layer on the product, say silicon. And the chamber is then again purged, and the atomic layer might again be modified by a plasma to allow chemical reaction with the next layer. And this goes back and forth, applying a single atomic layer each time in repeated cycles until you end up with a coating the thickness you're after. The good thing about ALD is it's often effective in layers as thin as 100, 200 nanometers. So you don't have to run these cycles too many times to get to an effective film. The films are incredibly dense with some of the best gas barrier properties available. The chemistry is specific and slightly limited compared to plasma as far as the precursors go, but the options can be tailored to very specific properties. So 3 things to know about material coating protection. Just to recap, we need to source a coating solution that meets our key performance characteristics: electrical, thermal, resistance to corrosion, moisture, and chemical attack, while considering the trade-offs in other areas. To select the best protection, consider the ingenuity of the end user and nature to find a way to break your device. You have to pick a coating that's going to protect against the unexpected. Bulk and weight. We need lightweight, thin coatings that are appropriate for small or weight-sensitive devices. They will not impede your design efforts and will allow smaller form factors. Heat dissipation. So thin coatings will dissipate heat better than thick insulators. And reliability. Field failures and sensitivity to defects. Conformal, durable coatings that are defect-free boost reliability. The best coating material increases value. It's going to increase revenue because a reliable coating material increases loyalty and sales. It's going to decrease costs because a good coating material reduces service calls and repairs, and it's going to mitigate risk. A good coating material prevents failure, thus preventing downtime, liability, and more. A few best practices to consider when designing for coatability or for protection. Placement. Design your board from the start to make protection easier. If you have a dual layer board, a stacked board, it's gonna be very difficult to dispense a silicone or a urethane on the components between those two boards. So design for that, or pick a coating for the design that you have. A vacuum coating is gonna be able to go all places. Also consider placement in your process. Panelized parts are easier to handle when it comes to an overall conformal coating process. You have to be concerned with the cleanliness in your factory and at which point in your process the conformal coating gets applied. Consolidation. Group the masking points, so areas that you need to have exposed post-coating. Group the components that you need to protect. Move your test points to support panels if possible. If you have a live signal plus holes in your coating plus the environment, you're going to have an unprotected board. So consider consolidating the areas that you have exposed and the areas that you have to protect in order to make it easier to handle. And consider components. Choose components that are appropriate for the protection level that you're after, or that are more easily masked. If you're going to have an IP-rated product, you're probably going to want an IP-rated switch or something that can handle a vacuum coating process. If water can't get in, generally a vacuum process can't get in either. So sourcing a component that meets your end goal, even if you're going to be protecting it with a vacuum process, is a good idea. Complex and blind connectors can be very hard to mask and very difficult to coat. So consider designing around that as well. Handling is critical to coating performance. This applies both to traditional conformals and thin film vacuum processes like we're covering here today. Adhesion of the coating to the substrate is going to impact performance. Cleanliness impacts adhesion. It also impacts corrosion. So as I mentioned before, all polymers breathe. If there's dirt under the polymer or dirt under the coating, the water molecules are going to get down there and they're going to stick to the dirt. And no matter how good your primers are, contamination is going to impact adhesion of your coating. Conformal coatings can cover a variety of sins from handling and manufacturing, but they are mostly delaying the inevitable if you have a dirty board. And that dirt can be flux, even something that's designed in your process, something you need. You need the flux in order to have a soldering process. But flux, reflow, and baking steps can all impact adhesion and the contamination level of your board, as can the time between SMT and coating. The time between coating and assembly, all of these things are going to impact your coating and its ability to adhere to the substrate. So I'm just going to put this up here for a minute for people to review. Here are some representative impacts to equipment, operating and consumer costs from failures and reliability hits. You probably recognize a few of these that are relevant to your industry. Downtime, repairs, returns, and ultimately brand reputation can all take hits from these things. And while conformal coating is often seen as a cost adder rather than a cost saver, these numbers tell a different story in the cost of ownership and the protection of your product and ultimate reliability out in the field. So what to look for in a protection partner? Concept development and design for excellence collaboration. You want to have somebody helping you with your conformal coating, either internally in your own departments or externally with a service provider who knows how to start from the beginning and help even with the design process and the ability to design a product for a protected end goal use. Sampling and pre-production coordination, so working with you hand in hand from development through the engineering builds up to mass production ramp. There's a lot of changes that need to happen typically. There's a lot of learning that goes into protecting a product from the design phase all the way through into manufacturing. So it's important to have a partner that can work with you in this. And production optimization, really dealing more towards your where in the line is this going to fit, where in my assembly process is this going to fit. It helps to have a partner who understands how they fit into the overall manufacturing and assembly of a product. So in closing, here's a brief history of HCO. We've been working on conformal coating for just about 10 years. We design and build all of our own equipment, which gives us control and knowledge of the full process. We have a firm commitment to R&D, advancing our mastery of paralenes and expanding into plasma and ALD deposited films with our spectrum of protection. It also helps that we have a global footprint, the United States, Europe, and multiple manufacturing centers in China and Vietnam. So yeah, I'll just leave this here for a minute for your review. I'd like to thank everybody for their time today, and I'm going to hand this back over to Stephanie to lead the Q&A.
Great, thank you so much, Dusty. Our first question is, you mentioned a couple examples of reworking for thick coatings, but if you want to rework parylene coated PCBs, what kind of solvents can be used to remove the parylene? Do you need a vapor degreaser to use them?
Good question. So parylene has a reputation of not being reworkable, primarily because it's very resistant to chemistries and attack from solvents and chemistries. So what actually works best for parylene is a thermal or physical rework. If it's just removing a small component, then typically the heat from the soldering iron is enough to melt the parylene away in that area, and it stays fairly localized. And you're able to replace the component and then touch up afterwards with a silicone or a urethane or epoxy of your choice to leave that component protected again afterwards. You can also use a physical removal method, such as grit blasting. You'll use basically a small sandblaster, but it tends to use a softer material such as a walnut shell, or even dry ice. You can get powder. You put the dry ice through a grinder, and it makes a small abrasive particle that doesn't damage the substrate, and that'll remove parylene pretty effectively in a small area, allowing you to rework your area or rework that component that you're after.
Great. Our next question is, aside from parylene, what specific types of coating materials does HCO offer?
HCO has been working pretty heavily in a number of different plasma solutions. So some of those are thick, some of those are thin, and I mean that from a standpoint of it can be a simple surface modification to improve the hydrophobicity of your product. A lot of times that's enough to get to an IPX4 kind of rating on the IPX scale, meaning it's splash resistant, helps to shed the water away. We have some thicker coatings that are capable of immersion protection from the plasma side. And we've been working pretty heavily on some ALD, low temperature ALD coatings that we should be able to offer in the near future.
Fantastic. Keeping with the theme of ALD, our next question is, what material can HCO provide with ALD film?
Sorry, what material, as in content or actual material types? And I don't think you're probably going to answer that. But I'll give a broad. So on our website, we do have some information on our ALD processes. But we're working with a number of different materials. Typically, those are alumina or silica, or occasionally titanium. So it's going to be typically a ceramic coating that goes down from the ALD process.
Thank you. Thanks for answering a little bit of both there.
Okay, sorry.
Our next question is about Parylene materials. So regarding fluorinated paralenes, would any of them be classified as PFAS substances?
Yes, so the fluorinated ones are considered PFAS because they don't actually release to the environment. As in when they're fully polymerized and the fluorine is not free to react.
Great. Our next question is, how does the PECVD process compare to the Parylene process?
So PECVD tends to be shorter duration, meaning that for a Parylene process, if it's 4 to 12 hours to deposit the coating that I need for a given protection level, the plasma process, PECVD, is going to be 30 minutes to 120 minutes. The chambers tend to be slightly lower in loading efficiency, but because they're a little bit faster as far as the coating goes, that's going to be, they balance out. The range of materials available from a PECVD coating is slightly broader. You tend to do multi-material stacks there instead of just a single Parylene material. And so you end up with a bit of tailoring that goes on there as far as picking the various chemistries you want, depending on the surface features or the barrier properties that you're after. I think that answers the question.
I think so as well. In what time frame does corrosion start affecting a PCB?
Corrosion can start to impact a PCB immediately. It may not be visible and it may not have an impact on electrical properties or signals immediately, but the metal at the substrate starts to react as soon as it's exposed to water and ions and voltage. Typically, this shows up first as just a bit of oxidation, but the dendrite formation can start to occur in as little as 10 minutes in a way that is capable of forming shorts.
Great. How specifically does HZO drive down the cost?
So HZO has been working for a lot of years in masking and demasking, which is typically seen as one of the more expensive parts of doing a conformal coating process, particularly a Parylene conformal coating process on your product. We work at volume. We work with automation where it's appropriate. We use materials that have known performance characteristics. So we source our masking materials in such a way that we don't have to use too much of them in order to get the adequate masking. Couple that with the ability to automate the application, automate the inspection, and that drives a lot of the cost out of the available cost out of the masking and demasking of a product. Helps to have a lot of knowledge in how to develop a solution for that too, knowing exactly what needs to be masked and what way, whether a plug is more appropriate than a chemical maskant or a tape. Additionally, our Parylene chambers are large, which helps with throughput and efficiencies. We're able to utilize less material per product and less cycle time per product in order to get things processed and coated and protected.
Great. And so with that, what happens if the coating is applied on a PCB containing some electromechanical components, something like a button? Will they be protected against the water damage as well?
That varies a bit. So moving parts are problematic. They typically need to be masked because you don't want Parylene to get inside the moving part. I mentioned briefly that if it's, for instance, on a switch or a motor or a vibrating motor, such as you might have on your watch or your phone, if it's an enclosed housing and it's IPX7, then you're not going to get coating inside that. So it's not a problem there. But on a big moving switch and things like that, we typically need to mask those so that the conformal coating doesn't get inside, which is the same thing that you have to do with any traditional conformal coating as well. You can't get the coating inside those. You can't get silicone inside your switch. And yeah, so it would be a risk point because it's not sourced to be an IPX7 or IPX4 component, but it is mostly protected by the coating that's on the outside.
Okay, great. And then our final question for the day, and any additional questions we'll follow up with via email individually. Again, as I said, we're going to be sending out the recording and the slides as well. So if you think of questions, you can always feel free to reach back out to us. But when do you choose nano coatings over Parylene, and when do you choose Parylene over nano coatings?
That's a really good question, and it ultimately comes down to product and the customer's end goals for protection. So each of the types of coatings, Parylene versus nano coating, have their strengths and weaknesses, and they have their areas where they're best applied. If it's something that has a higher protection level, I'll often choose Parylene. Parylene being kind of the gold standard. It protects better, longer against full immersion, against exposure to harsh environments. If there's mechanical tolerancing concerns, meaning I don't even have the 20 microns or 10 microns that I would normally use for Parylene as far as space goes, then I need to consider a 1 micron plasma coating, for instance, or even a 200 nanometer ALD. So mechanical tolerancing comes into play. Desired surface features of the final coated product, whether it needs to be hydrophobic or hydrophilic, or there's a number of different ways that weighs in. So yeah, it ultimately comes down to what's the end goal and what's the product itself.
Fantastic. Thank you, Dusty. With that, we're going to close out for today. Thank you all so much for joining us. We hope that you learned a lot about the different things that you need to know in order to engineer reliability into your electronic product design. These slides and the recording of the presentation will be sent out to you later today, and we hope that you have a good rest of your day.